All right, let's get right into it. Have you ever stopped to think about what actually makes your favorite apps work? You know, what makes them so snappy and seamless? Well, today, we're pulling back the curtain on the secret engine that powers, well, pretty much the entire tech world. Data structures and algorithms, or as you probably know it, DSA. If you're in tech, you've heard this 1,000 times, right? To get a job at Google, Meta, Amazon, you have to master DSA. But why? What is the big deal? Why is every single one of these companies so completely obsessed with it? You know, when it comes right down to it, it's all about one thing: money. Yeah, every single time you tap a like button, search for a friend, or even just scroll through your Instagram feed, that action, it costs Meta real money for the computation power.
Now, look, a tiny fraction of a cent per query. That sounds like nothing, right? But think about it. Multiply that by a billion users doing billions and billions of actions every single day. Suddenly, you're looking at a jaw-droppingly massive expense. So how on earth do they keep that from spiraling out of control?
And that is exactly why these companies are desperately looking for engineers who get DSA. See, it's not about being able to solve some weird, abstract puzzle. It's about being able to write smart, efficient code that saves the company millions, sometimes billions of dollars.
So what is this magic toolkit we're talking about? Well, it really starts with a simple idea: the difference between just having raw data, a complete unorganized mess of information, and having a well-organized, super efficient data structure.
A data structure is basically just a way to organize your data. I mean, think about it like this. You could just dump 1,000 books into a giant pile in the middle of a room. Or you could organize them on shelves by author and genre like in a library. One way is chaos. The other makes it incredibly easy and fast to find exactly what you're looking for.
And the algorithm? That's the recipe. It's the step-by-step instructions your code follows to take all that nicely organized data and actually do something useful with it, to solve a problem and get a specific result.
So what's actually in this developer toolkit? Let's go on a quick tour of the fundamental data structures that, honestly, every software engineer needs to know like the back of their hand.
First up, the most basic one, the array. Just think of it as a row of boxes, all in a neat line. It's incredibly fast to grab something from, say, box number 5, because you know exactly where it is. But if you want to add a new box in the middle, you have to shift everything after it down just to make space.
Then you have the linked list. This is more like a chain. Each item, or link, holds a piece of data and a pointer to the next link in the chain. It might be slower to find the 100th item because you have to follow the chain, but inserting a new item is a piece of cake. You just break the chain, pop the new link in, and reconnect it. Easy. Next, we've got a stack, and it works exactly like it sounds. Think of a stack of plates. You put a clean plate on top, and when you need one, you take it from the top. The last one you put on is the first one you take off. That's why we call it LIFO. Last in, first out. Your browser's back button? Classic stack. The opposite of a stack is a queue. And again, it's just like a real-world queue, or a line. The first person who gets in line is the first person to get served. First in, first out, or FIFO. This is perfect for things like managing print jobs, right? The first document you send to the printer is the first one that prints.
And finally, let's talk about the tree. Now this one sounds complex, but I promise you use it every single day. It's just a way to organize data in a hierarchy with a root and branches. The best example, the file system on your computer. You have a main drive, then folders inside that, and folders inside those folders. That's a tree structure.
Okay, so we've got all these different tools in our toolkit. The million-dollar question is, how do you know which one to use? Well, to really see why this choice is so important, let's talk about something we all care about: speed. Okay, imagine this scenario. You're given a massive phone book, and it has 1 million names in it, all sorted alphabetically. Your task is to find one specific name. 1 in a million. How would you even start?
Well, one way to do it is what we call a linear search. You could just start at page 1, check the names. Not there? Go to page 2, check the names. Page 3, page 4. You just go page by painstaking page until you find it. Now, this approach is simple, I'll give you that. But it is painfully slow. I mean, what if the name you're looking for is at the very end of the book? You might have to check almost 1 million names just to find it. Talk about a waste of time.
But what if we used a much smarter algorithm? What if we used a binary search? With this, you open the book right to the middle page. You look at the names. Does your name come before or after this page? In one single move, you've just thrown away half the book. 500,000 names, gone.
And you just do it again. You take the remaining half, go to its middle, and chop it in half again. You keep repeating this, and what could have taken you up to 1,000,000 steps with the first method now takes about 20 steps total. That is the incredible, game-changing power of using the right algorithm.
This crazy difference in speed is what we measure with something called big O notation. For that slow linear search, we say its complexity is O of n, meaning the time it takes grows in a straight line with the amount of data. Double the names, you double the search time. But for binary search, it's O of log n. That means if you double the number of names, it only takes one extra step to find what you're looking for. It's a massive, massive difference.
And you know, understanding these trade-offs, knowing which tool to grab for which job, that's what separates someone who just writes code from a true software engineer. So let's see how this all comes together in your toolkit.
So you see, your DSA knowledge isn't just some theory you learned for an exam. It's a real practical toolkit. It's what you use to build software that is better, faster, and as we talked about, way more cost-effective. At the end of the day, mastering DSA is all about being able to look at a real-world problem and make an informed decision. To know exactly which tool to pull out of your toolbox to solve that problem in the best, most efficient way possible.
So I'll leave you with this final thought. If someone hired you today and said, build the main feed for our new social media app, where would you even begin? Which data structure would you choose to power that feed? And more importantly, why? The answer to that question could be the difference between a billion-dollar company and an app nobody ever remembers.